This is part 4 in a series of videos in which I'm attempting to repair a Wren executive system computer. Now, as ever, unfortunately I haven't been able to locate any technical information about this machine, so I don't have any schematics, I don't have any information about the boot up sequence or the way this is configured. So I'm having to play this by ear and make it up as I go along. If you've watched the previous videos in this series, you know that I corrected an issue with the power supply. And also I've replaced the DRAMs, a lot of which had failed. And I had a poke around looking at various things, and so far what I've discovered is that while the processor itself, and this is a Z80, is actually running, so there is activity on the data bus and address bus, most of the other peripheral devices are doing absolutely nothing, and the data buses going to them are floating. In other words, the buffers that are used to drive them are never being enabled. So there's a hardware fault, or there's something wrong with the initialization of the system. And because I don't know what the initialization sequence is, it's quite difficult to start fault finding. Really, when you encounter something like this, it's devising a plan of attack. And as I say, what I normally do with the Z80 is have a quick poke around the control lines, and what I've found with this one is that the interrupt line, which is active low, is permanently low, which is a bit suspicious. Normally that would be high, and it just strobes low whenever a device wants to generate an interrupt. I've done a bit of tracing around. I haven't spent a lot of time on this yet, but I've done a bit of tracing around and found that the interrupt line is fed from a priority encoder. So it's an 8-bit priority encoder, and essentially the way this thing works is it has 8 inputs, and depending on which input is active, then the output will go low. The output is fed through to the interrupt line of the Z80. So in other words, this is kind of a fan-in system for various devices to be able to generate interrupts. And that is in turn, or at least the input that is currently active. So I checked this and it's working fine. I use the logic comparator. This device, it's a 74148, is working fine. One of the inputs is in fact active, which is why the interrupt line is low. And I traced that back through, and it's actually being derived from the floppy drive controller chip. So that's this output on this device. So that should be low, and it's high. There is activity on the inputs, so we have a possibility here that this device could be faulty, or one of the floppy drives could be faulty, and the machine is just not smart enough to be able to continue. What I tried doing is removing this device, but when I do that, oddly the Z80 doesn't run at all, which is quite strange. I tried lifting the interrupt. This is the interrupt request pin that's causing this, as we might expect. I tried lifting just that one pin, and while the Z80 does then run, and the interrupt is no longer present, it doesn't get any further. We don't see any difference on the machine, and it still doesn't access anything. So it might just be that this device is faulty and the Z80 won't progress beyond that point. So once you come up to something like this and you don't have any technical information, the approach that I take is to have a quick look at the architecture of the machine and decide on the best plan of attack. So if you are not familiar with the Z80, it's a 16-bit or 16 address bit machine. It's an 8-bit processor, but it's got 16 address lines, and that means that it can address up to FFFF in hex addresses. So in other words, 64K of address space. If you look at the spec for this Wren, you'll see that it supports up to 256K of RAM. So straight away we know that this machine must use bank switching for the memory. Also, if you're not familiar with the Z80, it's got quite a nice feature in that the in-out is effectively mapped into a different space within the device to RAM. So in other words, it effectively can address more hardware outside of the normal memory space. Even so, that doesn't give it enough address space to be able to directly address the amount of RAM it supports. So it must use bank switching. Of course, I don't know how the bank switching is arranged on this machine. I was asked a short time ago whether I use a Fluke 9010A, which is an in-circuit tester, for this type of machine. And I do have one. I don't use it that often because it kind of needs the target machine to be working before it will really work itself, which kind of defeats the purpose to a large degree. But it is very useful for doing some types of testing. While I wouldn't normally use it at this stage, I'd normally at this stage go straight onto the logic analyzer. I thought you might find it interesting if we just connected the Fluke and see what it makes of the system. It's got a learning option, so what I'll do is I'll get the Fluke connected and then we'll run it through its learn option and see what it can make of the system. Bearing in mind we know it won't be able to detect the entire memory space because the bank switching will require active processor commands to make those banks available, and the Fluke is only connected to the Z80 socket, so it's only going to see the default memory address space presented to the Z80, but that should still show us whether the system is fundamentally working or not. So I'll get that connected, get back on camera, and then we'll run the Fluke and see what happens. Okay, so I have the Fluke connected. As you can see, it plugs directly into the processor socket. If you're interested, I sell these as bare board kits on my website, and as I say, they can be useful for certain types of testing. And we'll look at this as we go through the repair of this machine to show the various things that it can do. But the first thing I'll do is take it through a learning cycle and see what it can detect on the target machine. So I'll reposition the camera so we can see the Fluke, and we'll give it a run. Okay, so we're looking at the Fluke. I'll power it up. I'm not sure if the display will be flickering on camera. If it is, it's just due to the camera shutter speed. It doesn't actually flicker in real life. I have the pod connected to the target board, as you saw. I'll power up the target board. So the target's now powered up. Of course, it's not running because the processor is no longer fitted. What we'll do is some basic testing before we start a learn process. So I'll try do a bus test, and as you can see, the bus test is coming back as fine. What the bus test does is it just checks the active control lines for the Z80 and makes sure that those that should be switchable can be switched, and the others are in the state that you'd expect them to be. By default, the Fluke doesn't take any notice of the interrupt line. So what we'll do is switch on the interrupt line and see if the Fluke can detect the fact that it seems to be stuck. So as you can see, it's currently set to no. Set that to on. And what we can now do is a bus test, but you can see that we have an active interrupt warning. So this essentially means that the microprocessor interrupt input is being constantly set, and you can see this is looping round and it's checking it over and over again, but the input to the interrupt line for the Z80 is constantly set. We knew that anyway, but this is one of the things you can do with the Fluke. So I'll turn that back off, and the rest of the bus test is fine. What I'll do now is, because I don't know the architecture, I don't know the addresses that certain parts of the system are at, or any of the system. So I don't know where the RAM is located, I don't know where the ROM is located. I suspect the ROM will be located from address 0 upwards, because the reset vector for the Z80 is address 0, so there must be ROM there or something that can redirect the Z80, and generally speaking that is ROM. But I don't know how the rest of the system is configured. As I said, we're only going to be able to see the first 64K of memory space and because the Wren almost certainly uses bank switching, we're going to get some fairly odd results, but we'll give it a run anyway and see what happens. So we'll go from address 0 and we'll go up to the maximum directly accessible address space that the Z80 can manage. We'll run that. Now this does take quite a long time, so I'll fast forward through this, but it will take probably 10 or 15 minutes to complete. And while it's doing that, I'll play you some music. Okay, so that took about 15 minutes, and as you can see, it's finished the learning cycle. It's gone through all the addresses in the space we asked it to, and it's checked to see if they're readable only, readable, writable, and which parts of the read and write bytes can be addressed, and from that it can determine whether it's ROM, RAM or in-out. So we'll start with the ROM. And as you can see, we have a block of ROM from 0 to 1 FFFF, and we've got a signature here and it's saying it's 1A02. I don't know if that's right or not. I'll compare it with the signature on the ROM programmer in a few minutes, but that's a good sign. It means that at least the processor seems to be able to access the ROM. Whether this signature's correct, I don't know yet. If it's not correct, it could be because there's an issue with the unit itself, or it could be that the ROMs themselves are corrupt. But we'll progress on the basis that's correct for now. We'll see if there's any more ROM addresses, and there's another block. It's identified here as 4000 to 4003F, and some other blocks. So it's saying there are 3 blocks of ROMs. A bit strange, but it could be they are registers within one of the devices that is sitting on the address bus. We'll look at in-out, see if there's any in-out space, and it's saying we've got in-out at EE09, F080, and various in-outs. So it's identifying in-outs. I'm not particularly interested in the addresses at the moment, but what's significant here is it means that it can both read and write to various memory locations. So now we'll look at RAM. That's probably the most interesting bit. It's saying there is no RAM information. So in other words, it has not been able to detect any RAM. That's kind of unusual. I'll point the camera back at the system board and we'll discuss that a bit further. Okay, so looking back at the system board, I'll get the Fluke out of the way. Okay, so the Fluke couldn't detect any RAM, that is, it couldn't find any memory locations in that first directly addressable 64K block that it could write to and read from in entire 8-bit chunks. And that could be because a single data bus line is not working, and it would identify that as in-out rather than RAM. But it wasn't identifying any solid blocks of in-out space either that would look like RAM, so it tends to indicate that the processor can't access any RAM space. Now, looking at the board, as I say, I don't have a schematic, so I've got no idea how this memory map works on this device. We have the 2 ROM chips, and I will check with the logic analyzer and see where they're mapped to. It looks like they are mapped to address space 0 up to 1FFF. However, they are 64K devices, so whether or not just a part of them are used or there's something else going on, I'm not sure at this point. The other devices we have on here that have storage, we have a real-time clock chip. This has a block of RAM inside. Whether or not that RAM is used in this device, I don't know at this point. We then of course have the main DRAM, and we also have 2 SRAM chips, and we have the video RAM. Now, what I was expecting to find in a banked system is that to make the system efficient, normally you would have some SRAM that is mapped across the entire address space, that is RAM that's available in all banks, and that just means that the software can be more efficient in that it does not have to switch banks to address certain important values that are in RAM. So I was expecting at least these 2 devices to appear in the memory space as RAM, and as you saw, there was no RAM detected at all. So it didn't detect this device, it didn't detect the DRAM, and it didn't detect these, and it didn't detect the video RAM. I'm not surprised about the rest of it, but as I say, I was expecting these 2 to appear. Now I have, as I mentioned in the previous video, I've taken these out and tested them, and they work fine. I will try a couple of replacements just to make sure that they're not marginal, and I'll run the Fluke test again, see if it can find them. But what I will probably have to do from this point on, as I say, I haven't been able to locate a schematic for this, so unfortunately from this point on it will get fairly complicated. I can start using a scope to look at the lines going into the RAM chips. I have looked at those briefly already, and the read and write and enable lines are changing, so it looks like the chips are being addressed. So it's possible we have an issue with one of the buffer chips. But what I'll do is I'll put a logic analyzer onto the Z80, and then we'll start looking at what the machine is actually trying to do. We'll see what addresses it's trying to access, and then we can also look at the read-write lines to see if it's trying to access ROM, RAM, and if so at what address. And then we can see what's being returned, whether or not it can actually successfully read and write to those addresses. Once we've determined what address the RAM space is at, I can then start doing more specific testing to see why the decoding is not working, or why it's not reaching that part of the system. It's still possible it's just simply a failure of something like the floppy disk controller, but it does seem very odd that that would prevent RAM from being accessed unless all RAM is banked out, but that would be a very strange thing to do, so I kind of doubt that's the case. But as I say, I'll put the logic analyzer on, and in the next video we'll see what we can determine with the analyzer, and try and figure out what's going on with this system. In the meantime, if anyone has a schematic for this, then please let me know.